right. Good morning, everyone. My name is Siamak Malemi. I'm a professor here at Columbia Business School, and I'd like to welcome you to this year's Columbia Crypto Economics Workshop on behalf of the Engineering School at Columbia, the Business School, and the Ethereum Foundation. You can view the agenda there or on the conference website. But before we get started in earnest, I want to go through a few housekeeping matters. First of all, please remember to silence your devices. Remember that there's no food or drink allowed in this auditorium. So all of our food breaks, including the coffee breaks and the lunch, will actually be in the first floor downstairs. That said, if you want to take some time in between sessions and have conversations and so on, be aware that there's an area outside with tables and so on that is very conducive for that. Also, you may have noticed there's a security desk to pass through and come upstairs. And to pass through that desk, you'll need to make sure you have a wristband as well as making sure that you get another wristband tomorrow. Finally, there are restrooms outside around the corner on this floor, and we will also have a group photo here in this auditorium before we break for lunch. So there's just a handful of logistical announcements. Before I introduce Dean Chang for some opening remarks, I do want to acknowledge the support that we have gotten from the engineering school and the business school for this event and for blockchain research more broadly. Both Dean Chang and his counterpart, Dean Maglaris of the business school, have been incredibly supportive over a long period of time. This is the third year we're doing this. It's not the only thing we've done. We also have a seminar series. We've had grant programs. We've had a number of other conferences. We've tried to have events that are multidisciplinary, on a number of axes, bringing together people from different fields such as business, economics, operations research, computer science, and also, like the event today, really bringing together the top researchers, both from academia as well as from industry, and really trying to leverage our location here in New York City, which I certainly believe is the hub of crypto today. This has really only been possible with the steadfast support of the business and engineering schools, which I'd like to acknowledge. And so with that, let me introduce Dean Chang for his opening remarks.
All right, good morning, everyone. I'm Shifu Chen, Dean of Columbia Engineering School. On behalf of my friend, Costis Manzanares, Dean of Business School, myself, welcome everyone to this workshop and conference. And I think this is the third event of this wonderful topic. And one thing really impressed me is really the multi-sector, multidisciplinary nature of the topic that we cover in this conference here. I was talking to Siamak and Tim here, is how wonderful that we are able to bring theoretician, computer scientist, business leader, economics, and also the practitioner and policymaker leader come to this forum to think about this wonderful new platform computing paradigm of a layer of a protocol reaching consensus. And there are so many new business models we can explore, no matter it's academic field or economic or societal application, beyond all the cyber currency we are talking about right now. Really wonderful to reflect the spirit of multidisciplinary collaboration as well as a multi-sector convergence. And that's what we are celebrating at Columbia University Engineering School, Business School, as well as many institutions in New York City. As Siamak mentioned, is a wonderful location to host a topic like this one here. At university, we have been launching a lot of cross-disciplinary collaboration, particularly engineering business school. Not only we have a lot of a joint degree program, we have a wonderful center like this, and also we have a new degree program, dual degree program between business school, engineering school, we call MBA XMS. So it's a 2-year program really combining the training and skill building for our student and practitioner after working for a few years, coming back for 2 years training by faculty in the engineering school as well as a business school. So students can develop the business leadership as well as the engineering foundation in the emerging area. So that's one example of cross-disciplinary collaboration that we are working on. I'm not sure we have any student from a dual degree program here. Wonderful cohort. This is the second year we are doing here. Fantastic. And there are other cross-disciplinary efforts we are also leveraging all broad skills in the university, 17 schools. So we have a new center on AI plus neuroscience, which is cross-disciplinary engineering school and neuroscience in the Zuckerman Institute, just the next door building. We also have a new center on AI and climate prediction, a new center on AI and digital finance funded by Capital One, a multi-year center. And this is very much in line with the vision and the mission of a digital finance center led by business school here, and also a new center on sports and AI. So these are so many examples that of the cross-disciplinary, multi-sector collaboration we are addressing in the conference like here before. And blockchain and crypto not only revolutionized the computation paradigm, also revolutionized the imagination of a new application. So that's why we feel so excited here on all the new courses, the new topic, the new academic papers, as well as the new business opportunity that we can explore in this space. So for that, let me thank a few people really put in a lot of effort to put this together. From Ethereum Foundation, David Krepis, Justin Drake, Barnab Monet, and Mike Nuder. I'm sure some of them are here for making this event possible. And particularly Siamak Malemi from Columbia Business School and Tim Roughgarden from Business School and also A16Z Crypto Research Center. So with that, I wish a wonderful event. I'm looking forward to another year of a very productive discussion and looking forward to more results of our collaboration here. Thank you very much.
Okay, thank you, Dean Chang. With that, we'll commence our first session. The topic of our first session is going to be MEV mitigation. And I'll introduce our first speaker, and that is Dan Robinson from Paradigm. Dan is probably familiar to most of you. He's one of the most prolific researchers in industry, and he's going to tell us about priority taxes this morning.
Thanks. So, hi, I'm Dan Robinson. I'm a general partner at Paradigm, and I'm going to be talking about priority ordering. But even more broadly than that, I'm going to talk about what I think layer 2s should do with MEV. I think this is a popular topic in part because a lot of L2s are thinking, should we be using MEV as a revenue source? Should we be trying to redistribute it and to fund various things? And my view on this overall philosophical question, which I think is really important for how we solve it, is that L2 sequencers and L2 platforms should not be trying to capture MEV for themselves. What do I mean by this? I think MEV's of minor extractable value is something that L2 sequencers can capture, and I think to date have been able to, and in some cases do. But in general, it leads to really bad user experience. When users are trying to actually interact with chains that capture their maximum MEV, I think that leads to users losing money, and it reduces the things that applications can actually do on that chain. I also think it's bad for the platform itself, in that it's an inefficient way to generate revenue. If a platform is guaranteed to capture maximum MEV, it's not actually going to, applications aren't actually going to be able to do all the things they'd otherwise be able to do, and we end up with some deadweight loss that reduces the revenue that an L2 sequencer can capture. Instead, my view is that L2s should enforce rules that allow applications to capture their own MEV. And I think in the long run, this is actually going to be best for the platform themselves. We see a lot of applications thinking about launching their own chains, splitting off from L2s, and that's often one of the reasons is that they want to capture MEV rather than having to go to the L2. And if the L2 allows applications to capture it themselves, then they may be able to keep all the benefits of being on a generalized L2 while still being able to avoid leaking that MEV. And I think this philosophy, which is important for priority ordering, it's also what we were thinking about in Unichain's approach, Uniswap's L2, their approach to capturing MEV, is that the chain shouldn't be trying to capture MEV for itself, it should be returning it to users and applications. And this is what Unichain is doing with the help of Flashbots and Optimism. And I think it pervades a lot of the philosophy that all three of these projects have been pushing for a long time in the space. And again, I think is really coming to a head with the Unichain project, which I'll talk a little about. So what I'll be talking about specifically is how I think L2s can support this really easily and painlessly. And the nice thing is that the solution for this is something that a lot of them are already doing, and that's called priority ordering. Priority ordering is just ordering transactions in a block from highest to lowest priority fee. And this turns out to be a really powerful primitive for applications on those chains to be able to capture their own MEV. It allows mechanisms like MEV taxes, which I'll talk about in this talk. It allows many kinds of application-specific sequencing, which is a popular topic, and generally allows making a lot of other ways to make MEV programmable at the application layer. And a really nice thing about priority ordering is that it's already used in production by most by many L2s, specifically any that are using the OP stack default sequencer out of the box. So Base, Blast, OP mainnet, and soon Unichain are all going to be ordering transactions by priority. And so you can actually program MEV taxes and other MEV capturing techniques in your applications on those chains today without any special support from the sequencer. And I'll talk about how you can do that. I think one really important caveat to this is priority ordering is not actually incentive compatible for the sequencer. So it is actually important for chains to be able to figure out how to make this trustless. And I'll talk a little about ways that I think L2s can actually enforce this trustlessly. Right now, L2s are running sequencers that are trusted for whatever ordering rule they're applying. And so the ones that are applying priority ordering, you can just rely on that to the extent you trust that sequencer. But in the long run, if we want to decentralize these sequencers, I think it's really important to be able to decentralize the MEV resistance on them as well. So I'll talk a little about that. And I think making it trustless is an open research problem, and there are many components of trustlessness for trusted sequencing. All right, so a little background. What do I mean when I'm talking about MEV? Because this isn't necessarily every type of what we've called MEV, or maximal extractable value. So it applies to many cases. So when there's competitive MEV available in a smart contract, there are agents out there called searchers that are often competing to be the first to grab it from the chain. And so when I say competitive MEV, I mean a kind of MEV that's accessible to anybody who can access the chain. So I think one of the most popular examples of this is top-of-block arbitrage on an AMM. If the price is changed on Binance, wait for the price to change on Binance, and then we'd be the first person to trade it on the AMM on chain. By default, usually on chain, all of this MEV is going to go to the sequencer if the application is written the way that most AMMs are today. And how does that happen? On a priority ordered chain, like Base, this typically happens through priority fees. So Base orders transactions from highest priority fee to lowest priority fee. And so if a searcher wants to be the first person to trade on an AMM, they will put as high a priority fee as they can in order to be able to access that AMM first. And so they're going whichever transaction succeeds and pays the sequencer is going to pay them the most of anyone who's competing for this. And if it's competitive, usually almost 100% of the MEV is actually going to go to the sequencer, not to the searcher. So by default, right now, priority fees result in Base getting most, or the L2 sequencer or L2 platform getting most of the MEV from this kind of opportunity. Now, the smart contract itself would prefer to actually capture this MEV. And so in the AMM context, we think about this as in the context of, as a concept of loss versus rebalancing, which is the losses that a AMM suffers from being arbitraged at the top of the block at the old price, or someone has to trade with it at old prices in order to move it to the new price, rather than trading at the new price with whoever wants to rebalance it. And the contract would prefer to capture this MEV. Usually in the AMM case, the contract would prefer that the MEV go to the liquidity providers, because that lets them increase the yield of the liquidity providers and get more liquidity, so ultimately benefiting the decentralized exchange. So I'm going to talk about a way that applications in AMM today on priority ordered chains can actually capture almost all of this MEV for themselves without having to get any special support from the sequencer. And this is a technique called MEV taxes. So the way MEV taxes work is, remember I said that in a priority ordered chain, transactions are ordered by this number, priority fee that's in the start of the transaction. that number is visible to any smart contracts that the transaction is interacting with. So what happens if the smart contract just looks at that number and can charge a higher fee based on it? Specifically, let's say they charge a really large multiple on it, say 99 times the priority fee. So what's going to happen is the 99% of the MEV that the searcher is going to pay, instead of paying it to the transaction fee, they're going to set a much lower transaction fee and pay a much higher amount to the sequencer. So we see back here, if they were going to pay $5 signs, the winning searcher was going to pay $5 signs to be ordered first. If that's their profit, what they're willing to bid, on the MEVTax application, they're going to actually have to pay almost all of that to the application itself. So they're going to have to set a much lower priority fee to be profitably included. If they set any higher priority fee than the small number, they're actually going to end up paying way too much in the MEVTax. And so all the searchers have to pay a much smaller priority fee to the sequencer and a much larger percent as a tax to the application. And so MEV taxes are a way to basically turn this priority auction that the chain is already doing into an auction that benefits not the chain, but the application or the users of it. I think it's important to note this isn't money that's coming from the searcher. This actually doesn't change searcher profitability at all. So here's just a diagram of how this typically works. In a normal priority auction on the left, the searcher has some amount that they are expecting to make in profit. That's the little green bar. And then some amount of available MEV that they know they're going to have to make as a payment. And they have to make this because they're competing with a lot of other searchers. And if they pay less than this amount, they're just not going to win the opportunity. So that light blue bar there represents the extra payment that they're going to have to make to basically win the opportunity. The question isn't how much profit does the searcher make. The question is, who does that light blue bar go to? And in the case of the normal priority auctions, almost all of that, or basically all of that, is going to go to the sequencer because that all goes into that priority fee. But if we set a MEV tax, that actually changes the searcher's behavior. And they have to set a much lower priority fee on the transaction and end up paying a much higher MEV tax to the application. And so the person who actually loses money, the incidence of this tax, is actually entirely on the sequencer, not the searcher. So this doesn't reduce searcher profitability. This just reduces the amount that sequencers make from MEV on their chain. So MEV taxes, I think, can be used for a lot of different kinds of MEV. I talked a little about how they can be used for AMMs to capture their loss versus rebalancing for the benefit of their LPs. But other examples, including one of the motivating ones, is DEX routers. So Uniswap X is an example of a smart order router where a user is able to auction off the right to fill their trade to anybody who wants to fill it on chain. And one nice thing about using MEV taxes for this is that you could have you have an auction on chain essentially for people to fill the order at the best price. So the way that Uniswap X would work with this is the order would itself have a MEV tax that would be applied to the transaction that fills it. And so the price of the order, the price when somebody fills a Uniswap X order that uses MEV taxes, would actually be a function of the priority on the transaction that fills it. So people are bidding to give the user a better price, and whoever is willing to give the user the best possible price ends up filling that order. And so this is actually live in production today with a small number of orders on Base. Uniswap has been trying out using Uniswap as the main way to fill Uniswap X orders on Base, and we're hoping to scale that up once we get more evaluation of how it's working. Some other examples, a lot of people have talked about Oracle extractable value. Right now, a lot of value of MEV comes from back-running Oracle updates in order to, say, liquidate a decentralized lending protocol. So if Oracles wanted to capture the value created by their updates, they could put a MEV tax basically on the transaction that includes the Oracle update. Alternatively, the lending protocol could use its own MEV tax to try to capture the value that would otherwise go to the Oracle. Finally, you could have a smart wallet that captures arbitrary back-running MEV, arbitrary MEV that can happen from any kind of user operation. And the way that would work is the user operation could be included by any transaction by anyone, and the MEV tax would be paid to the user by whoever actually includes it on chain. And so this would be if you just have a general purpose wallet where somebody wants to take some action, they're not sure whether there might be some MEV from back-running or even potentially front-running their transaction, and they want to actually capture that. And this would allow them to basically capture that, the MEV that they would otherwise emit by having searchers bid for the right to include their transactions. So that's MEV taxes. I want to talk a little about one of the other applications of priority ordering generally, because what I love about priority ordering is that it makes transaction ordering essentially programmable and accessible at the application layer. And one of those is for application-specific sequencing. I'm not going to use the acronym for that, but a lot of people have talked about application-specific sequencing in sort of different ways to design applications. And people typically think this requires special support from a sequencer, or special support from a chain, or even its own having to run your own consensus. And I don't think it necessarily does, as long as the sequencer on your chain is following the rules of competitive priority ordering. So priority ordering can be used to implement, for example, an application that wants to have a special kind of order book, where orders can be canceled before anyone is allowed to fill orders. And the reason you want to do something like this would be if market makers want to provide liquidity on an order book without being arbitraged and without having to race other fillers to be able to cancel their order and then end up having that end up leaking to MEV, we could do an on-chain order book. I tend to be an AMM person. I'm not a big fan usually of on-chain order books, but if you wanted to do an on-chain order book, I think you'd want to possibly do something like this, or at least this is an example of how you can use application-specific sequencing for it. And the way you would do this would be the application could actually define lanes within the block and say certain kinds of applications can only be included at certain points in the block. And so one example here would just pick some arbitrary number n and say cancels are only allowed to be included on a transaction that cancels any order on this order book is going to fail if it's included after that priority n, right? So the priority on a transaction that cancels an order must be greater than n. And then it could say a fill transaction, someone trying to trade on an order book, that transaction has to have priority less than n or it's going to fail. And what that means is the cancel transactions all don't have to compete with the fill transactions in order to cancel it. They actually can just, market makers basically at their leisure can just submit a transaction with priority greater than n, knowing that they're going to automatically outrace any fills. So they're not going to have to bid way higher in order to cancel their orders. And so that reduces the amount of MEV that active market makers on an on-chain order book would leak. So some of the benefits of priority ordering and MEV taxes. One is it's really easy to implement. And it can be implemented today in just a couple lines of Solidity. Basically, the contract just has to look at the base fee and the priority and the gas price on the transaction. From there, it can calculate, here's basically the priority fee, what the user bid, and I'm just going to charge the user an extra amount or change the price that I'm filling them at based on that number. So it's really easy to just implement directly in your contract. You don't need any kind of off-chain infrastructure. You don't need to have some off-chain auction being run. You don't need some special support from the sequencer. And most sequencers, by default, are just going to do this, most L2 sequencers. Specifically sequencers that are ordering by priority fee. There are examples. Arbitrum is the most well-known L2 sequencer that doesn't order by priority fee, but actually orders by first come, first served. And MEVTaxes directly aren't going to work on chains like that. But on any OP Stack chain today that I'm aware of, they all use the default sequencer, which orders by priority fee. I think it maximally retains composability and atomicity with other on-chain liquidity. And this is particularly important in the context of something like what I was talking about with order routing. So with Uniswap X today, so Uniswap X right now, the way it works on L1 is that there's one auction, sort of like RFQ, quote unquote, style auction to get the best possible price for the order from potential fillers. And then there's a separate auction, and people don't necessarily think about it as an auction, but it is, to actually get that transaction included on chain. And these auctions are not atomic with each other. So if you're bidding in the first auction trying to fill an order, you may not be able to actually fill that order on chain at the moment you were expecting to, and particularly against the liquidity that you were expecting to maybe trade it on. And this can disadvantage someone who's trying to compose this Uniswap X with things on chain, like route Uniswap X order flow to on-chain liquidity. So this is particularly useful, I think, for an auction like Uniswap X. If you want to bid on a Uniswap X order and say, I only want to fill this order if I can actually trade it on this particular AMM. And out of the box, MEVTaxes allow you to do that. But it does have some challenges. And I think the most important challenge to me in priority ordering is that it does require obedience by the block proposer or the block sequencer to these rules of competitive ordering, competitive priority ordering. So not only does the sequencer have to order transactions by decreasing order of priority fee, they also have to not censor any transactions. They have to not peek at transactions and use information they learned from that transaction to send their own transactions. And they have to not delay the user's transactions or be able to submit transactions that have a bit of a timing advantage relative to users. Like, say, like if the sequencer is able to construct transactions and submit them, even just like a 10 or 15 milliseconds after other users, that potentially changes the behavior of this auction and means less of the MEV would go to the user. So all of these things which sequencers today can do potentially would be able to undermine this mechanism. And enforcing these trustlessly, particularly as you would have to in a decentralized sequencer or in a context like Ethereum L1, is an open problem. So to be clear, today, priority order MEV taxes do not work on an L1 like Ethereum, where block building is dominated by this competitive process where generally block builders are trying to extract maximum value from blocks rather than following a deterministic rule like priority ordering. And particularly today, the way that they would undermine this would be transactions just wouldn't be included if they're even if they set a really high priority fee, if they're competitive with something that the builder wants to do. So another challenge with this is that failed bids, meaning if somebody bids on a Uniswap X order but their transaction reverts, that ends up resulting in a reverted transaction on chain. So everyone other than the top bidder on an auction, like the one I was describing, would end up paying a little bit of priority fee to get their transaction included on chain. And this could be prevented potentially by special support in the sequencer. I have a paper with CMAC and some folks from Uniswap on how revert protection as a feature of a chain, which is something that Unichain is planning to provide with the help of Flashbots. Revert protection actually changes the behavior of this auction and makes it a more competitive auction for users and for the sequencer. But you don't necessarily need to have full revert protection to be able to prevent this. There may be ways to have special support in a sequencer specifically for revert protection for MEV tax orders. And I think that might be a slightly simpler technical problem than providing revert protection in general. But that said, then we're in the space of providing special support from the sequencer. So it's true that by default today, so on chains like Base, which recently has had a reverted transaction problem, you might actually end up with a lot of reverted transactions if you're doing auctions this way. So that is a concern. And finally, or additionally, apps that use MEV taxes generally going to have very low priority fees. As I said before, if you have a MEV tax, that's going to cause the searchers who are trying to bid on your transaction to set very low priority fees because they're getting taxed for a large multiple of that. And that means if blocks are full, likely nobody's going to be able to interact with that application. I think that's a relatively small problem today. When I last checked, this was about 0.3% of blocks on Base had less than 1 million gas available for users to use. But it is a potential problem, and I think there are ways to maybe change the mechanism or the way that transaction fees work to fix that. But again, now we're adjusting the simplicity of the mechanism. And then finally, when you have multi-app MEV, when you have MEV that requires interacting with multiple applications, that does result in interesting games between applications and complex issues in who we're going to attribute this MEV to and what actually happens in the MEV tax world. This is more complex than I can get into in this talk. But also, I think it's kind of inherent to any attempt to do composable solutions with MEV capture is when you have MEV that involves interacting with two different applications, how does it get split? And I think there actually are some interesting equilibria potentially in how different applications will end up splitting MEV. But that's a little beyond the scope of this talk. All right, so I think the biggest topic and one that I'm really interested in further research on is how do we enforce priority ordering trustlessly? And to me, this is actually important for the project of decentralized sequencing, not just if you want MEV taxes, but if you want to have decentralized sequencing at all. And the reason for that is that I don't think L2s are going to tolerate the MEV situation that we have currently on L1 today, or anywhere close to it. I don't think L2s and their users are going to decentralize their sequencers if it results in a MEV free-for-all where you have a basically rotating set of proposers that are individually maximizing extraction from each block. I think that just reduces the user experience of using these chains and the experience for applications too much. I think they won't stand for it. So if we want decentralized sequencing, and I really do, I think we have to solve decentralized MEV protection. Otherwise, we're just not going to get L2s to decentralize their sequencers. So how do we make this actually trustless and enforce it trustlessly? And in my view, the project of decentralized sequencer actually should start with making existing L2 sequencers MEV resistant, basically preventing them from extracting MEV from their users and applications. The first and maybe simplest, but still quite complex challenge is censorship resistance. And this is a topic that's been talked about by Resnick, Pai, and Fox, among others. The importance of having censorship resistance if you're going to do any kind of on-chain auction. And MEV taxes and other priority ordering applications are a type of auction, and you really need to have the ability to force transactions into a single block, into the same block, in order to be able to use MEV taxes effectively. And so there are some interesting proposals out there for how to do censorship resistance. Inclusion lists are one example. It's been studied on the L1 layer, but potentially could be applied on L2. A similar version of this is called multiple concurrent proposers, proposed by Resnick, Pai, and Fox. I think is a really interesting mechanism. I think the key here, and what's really important for censorship resistance, is you need to have same block censorship resistance, and you need to basically be able to force a transaction into a block and force particular ordering. If you have priority ordering along with censorship resistance, that actually gives you a much better auction potentially. The next requirement of competitive priority ordering to make things like MEV taxes work is pre-transaction privacy. If somebody submits a transaction, we need for the sequencer not to be able to peek at their transaction and then be able to construct transactions of their own. And the reason we want this is if the sequencer can look at transactions, they can basically see other people's bids in this auction, and that causes a lot of different types of auctions, especially in combination with a little extra information asymmetry. That causes a lot of auctions to degenerate. So it's really important, I think, for users to be able to submit transactions that can't be censored and that the sequencer can't see and use to construct their own transactions before they actually confirm them and commit to include them in the block. There are a lot of possible ways to enforce pre-transaction privacy. I think one interesting one is threshold encryption. We have a group of people who need to all commit basically to the block before it can be decrypted. There's trusted execution environments, TEs, and that's something that Flashbots is working on, helping Unichain with their Rollup Boost product. And the other ideas like commit reveal or time lock encryption. I think there's a lot of potentially cryptographic ways to do this, but it's an open area of research right now. But it's really important basically to get trustless priority ordering to work. And finally, we want to reduce the timing advantage that a sequencer or any special party has in getting transactions included, their ability to delay other users or get transactions included after other users. And this is important because if they have a last mover advantage, even if they can't see your transaction, if they have better information about the outside world, they might be able to outbid or selectively outbid other participants in an auction in a way that potentially could cause the auction to get a worse result. Or cause other bidders to have to shave their bids in order to still be profitable as bidders. So making this auction work, generally you want to reduce as much as possible the extent to which there's a leader who has a last mover advantage. And this is a very difficult problem. And I've worked on it with my colleague Dave White and the Sorella team with a design called leaderless auctions. Which has, I think requires some strong assumptions about network synchrony and also a lot of rounds, but is one attempt at trying to reduce the last mover advantage that is inherent in a lot of consensus protocols. Max Resnick and some co-authors have worked on a proposal called Braid, which is an alternative way of trying to reduce last mover advantage in consensus. But again, I think this is an active area of study, and in my view, a really hard problem to solve in a decentralized network. Luckily, I think we can tolerate some last mover advantage without the system degenerating entirely, and working on a paper with some colleagues trying to quantify exactly how bad last mover advantage is. So in my view, this is a really important area of research, trying to reduce the MEV that L2s can capture. And would love to hear from anyone who's working on any of these particular problems. Great. Thanks, everyone.
We have time for some questions. There's some mics up here. Can we have the mics turned on?
Thank you for the talk, Dan. So one question around how to set MEV tax. You already mentioned that essentially, at times of congestion on the chain, these transactions may be priced out, and you mentioned is like less than 1% of times, but arguably is very correlated with the times when there is like most MEV. So I was wondering if there is any work around like potentially setting like dynamic MEV tags or things like that.
Yeah, if there's a way, and I haven't looked deeply into it, if there's a way to tell that blocks are full and adjust your MEV taxes based on that, you might potentially be able to sort of have it degenerate less in that context. I also think my preferred solution would be to somehow separate fees for getting transactions included on-chain from fees for getting transactions ordered on-chain. And in that case, actually, because you'd only want to charge a MEV tax basically on the priority fee, not on the inclusion fee. Right now, on all L2s that I'm aware of, they use priority fee as also basically the inclusion fee, so they order transactions by priority. But I think what we'd prefer would be if there was actually a separate number maybe for an inclusion fee, or you could consider using max base fee or something like that for that, where you could bid much higher to be included, but you're not actually bidding for priority. I think there's other benefits potentially to constructing, to changing the transaction fee mechanism that way. But I have not studied that, that idea deeply, so I would also be curious if other people have thoughts on that.
Thanks.
Thanks.
Okay, if there are no other questions, we'll move on to the next speaker. Let's thank Dan again. So the next speaker is Itamar Reif. Itamar is a core developer at Astria, and he's going to talk about lazy sequencing rules.
Can you hear me? All right, yeah. So hi, I'm Itamar. I'm a researcher and core dev at Astria. Astria is a decentralized sequencer project, kind of in the Celestia ecosystem. Okay, yeah. Today I'm going to talk about kind of implementing sequencing rules for rollups, and the lazy part refers to the fact that like this is a lazy blockchain infrastructure. So kind of for background, I'm going to give a bit of rundown on what sequencing rules are, although like Dan gave a pretty good explanation on what that is, and then explain what the lazy part is, and then I'm going to kind of run through how our system works, and then how that enables rollups and applications to leverage sequencing rules. So sequencing rules is kind of a paradigm that's emerged in the past, I'd say, like couple of years, for constraining kind of the effect that sequencers have on the value that's leaked by through the MEV supply chain. And I think Dan gave a pretty kind of good summary of how and why that happens and why that's of interest to people. But the TLDR, right, is like transaction ordering is like kind of the important aspect of financial applications, and the MEV supply chain refers to like kind of the off-chain actors that data flows through before it's actually like finalized by consensus. And so intermediaries there are able to kind of extract rent. And so kind of explaining what the lazy aspect is, this is a diagram of, I think, the Arbitrum setup, which is an example for like an eager or ahead of time sequencing architecture, where kind of the important thing to note here is that transactions reach the sequencer, at which point the sequencer computes a block, executes all the transactions, and creates a header for the block before the data is posted to consensus, and then consensus comes over the header for the block that is produced. And so there's kind of the transactions that go in the order that they were executed, and the state transition that resulted is kind of baked into what happens in consensus. Lazy blockchains generally are different in that consensus only happens over the data and kind of the shape of the data. So, you know, like these bytes in that order. And kind of there's two aspects to why this is advantageous. One is like you're only coming to consensus over kind of like opaque bytes, and so you don't have to execute anything. which allows you to kind of process many rollups at once. And so like the way to think about this is kind of pushing the execution to the edge nodes of the rollups that then like read data that was that we had consensus over. So kind of going to go through a high-level view of how the Astria system works. You start out with like the rollup node kind of at the top, and then you have a sequencing network and a data availability network that the rollups leverage, where the sequencer network is us. It's a Columbia FT chain with single solve finality, with kind of nice aspects like native bundle support, works with kind of multiple rollups at once. Because it processes opaque bytes, it's also like VM agnostic because the state transition function is kind of like pushed to the edge nodes that are the rollup nodes. And the rollup nodes interact with this like through, we like to think about this as like there's a write path and there's a read path. And so users send transactions to the rollup. These transactions are then bundled up and submitted to the sequencer, which includes bundles and comes over consensus of like what are the like transactions in a block without actually executing them. This data then kind of works. It's leveraged in two ways. We refer to this as like soft and firm blocks or soft and firm commitments, finality, that kind of thing, where like soft commitments are only kind of finalized on the sequencer, soft blocks are only finalized on the sequencing network, whereas firm commitments are finalized on the data availability network. And I'll go into what the different trade-offs there are kind of later on, but at a high level, like the sequencing network is able to like have a much smaller validator set and operate on much faster block times without kind of sacrificing liveness guarantees that you would get from a much larger network, specifically like Celestia, which has support for data availability sampling, which kind of lets it process very large blocks over a pretty large network without sacrificing too much performance. So kind of at a high level, the write path, which you can think of as essentially like the MEV supply chain in some respect, where you start out with a rollup transaction, which is then serialized into just kind of opaque bytes and then put into bundles, where like a bundle can be like a vector of like byte vectors kind of thing. So you can have multiple transactions serialized into a single bundle. These bundles are then posted to the sequencer, which creates blocks. The blocks end up looking like namespaced blobs, where each blob is going to be like the set of transactions that were sequenced in that namespace kind of thing. And then because we have this like dual finality mode where like the sequencer block time is much shorter than the data availability layer, we end up like batching several sequencer blocks into a single like blob posting on the data availability network. And so you get kind of every few sequencer blocks. I think the ratio right now is like 6-to-1 or 7-to-1. It changes, not deterministic block times kind of thing. But you end up batching several sequencer blocks into one kind of like data availability block. And so kind of what are bundles? Bundles have kind of a few important aspects. Essentially, you're posting serialized rollup transactions as opaque bytes that are namespaced by the rollup ID. And so because you have a vector of these and they're kind of namespaced by a rollup ID, you can just have like as many kind of rollups in one bundle as you want. The sequencer also has some like native functionality like transfers, working on like staking and unstaking, that kind of stuff that's very basic. And Celestia has a very similar kind of minimal functionality model where you just kind of post bytes and you can do transfers on the chain, and the rest is kind of pushed to the execution rollup nodes layer. There is kind of one gotcha here where like you end up with transactions on the rollup, but then also transactions on the sequencer. And so we have this kind of like gas station protocol that allows rollup users to pay kind of the bundling fees or sequencer fees with their like rollup wallets. And not going to go into detail around there, but that is like kind of an important thing to keep in mind. The way sequencer blocks work is also like kind of very similar. You have, very similar to the data availability layer, you have these bundles, which will have, like each color is a different rollup. So you'll have like the blue transactions, the red transactions, the green transactions. They're all submitted as kind of different bundles. These end up getting split into namespaces, and then that kind of gets finalized as like, this is the header, these are the blobs, and like some Merkle inclusion proofs of each blob and that kind of thing that allows us to like retrieve a rollup specific block, like a filtered block, without getting the entire block that was sequenced. And yeah, so kind of to talk about the soft versus firm blocks, soft blocks are finalized by the sequencing layers validators, firm blocks are by the data availability layer. The main difference is the block times and the validator sets. And again, the soft blocks are kind of batched and then posted to the DA layer. And the DA layer, like the nice thing about it is it both processes a lot more data and has a much larger validator set. And so the much larger validator set gives you like a much better kind of liveness guarantee, but there's also an important aspect that is data availability sampling and the light clients that can leverage that, which essentially allow you to like, you can verify that data was included in a block without retrieving the whole block, and you kind of get like a log n boost, speed up on the amount of data that you have to like retrieve from the network. So a rollup node can run very efficiently by only kind of querying the data that it needs from the larger network without kind of caring about any of the data that anyone else has posted there. And then yeah, this is kind of what the data that's posted to the data availability layer looks like. Where you have like several sequencer blocks. I think I have this written out as 6 blocks, 6 sequencer blocks in one, where in each one you have like the blobs for each rollup and the header for the sequencer, which includes, actually I should probably say like sequencer blob because it also includes some of the like sequencer side transactions, like the Merkle inclusion proofs for each of the blobs and so on. Each rollup's data ends up getting namespaced on the data availability layer as well. So when you talk to the data availability layer, you can say like, I just want my rollups data. And then yeah, you can like retrieve that with the data availability sampling, and that's kind of very nice. The other side of this is the what we call the read path, and you can think of this as like kind of abstracted away the difference between like data availability and sequencing layers, because you're like, from the rollup node's perspective, you're like processing these by kind of like sequencer blocks, because that's kind of the, you can think of that as like the fundamental like clock time of the network. And so like every 2 seconds you're producing a new block. You may be batching them and posting them to like a wider network every like 12 or 13 seconds. But as you're executing them, you're processing them kind of by the like 2-second block as like the atomic part. I don't know if atomic would be the correct word. But essentially, yeah, you get a block. You feed that into what we're calling like the derivation function, which kind of manages these like firm and soft commitments. It does the inclusion proof validation and extracts kind of the rollup data from that. You can think of this as like a kind of a light client to the sequencing and data availability layers that retrieves the data and then like feeds it into the rollup as kind of like transactions to be processed. And so you get kind of, you feed into the execution engine, which you can think of as like the rollup execution node or like Geth or that kind of thing. You just feed it kind of a bunch of opaque bytes, and then that deals with like deserializing it, executing it, and so on. And so kind of a nod to Dan's talk name. But so we kind of talked about liveness with the soft and the firm blocks, where you can kind of choose your which mode of liveness you care about, where like you can work with a the smaller validator set and get kind of a faster block time but a weaker liveness guarantee. You can work with the larger validator set, the data availability sampling, get a much better kind of liveness guarantee. The other aspect that's important here is safety. And safety, again, like determinism is all you need to get safety, because like the idea is like this data was made available, anyone can get it, as long as you like execute the same thing, you will end up with the same block. That may not be the most formal explanation, but kind of intuitively that's what's happening. And you can break down this, this pipeline here into like you get the block data, you do all these, like client verification, Merkle proof inclusion, Merkle inclusion proof validation, that kind of stuff. You're operating on opaque bytes because you're like, these bytes were just included in that sequencer block. From there, you're like deserializing this into the rollup type of data. And so, like think about it, this is like you have an ETH, like an EVM change, so you're going to deserialize this into like ETH transactions. And then you feed these into the state transition function, which then kind of gets a bunch of transactions in an order and produces a header and like a rollup header. You can kind of consider your like block executed at that point. The fact that all you need here is determinism is very useful, because you can kind of add an extra intermediate step here, which is executing a sequencing rule, which would be something like, like all the, I guess I'll just get the next slide. Like if you want to do something like priority fees, so you'll get a bunch of transactions, each is going to have their own fee. So like 0, 1, and 2 is going to have like 5, 3, and 7 as the fees. And then you kind of execute like a deterministic sort on this. That's like, I'm going to turn this into like 7, 5, and 3 and execute them by that order. And this is kind of a very powerful primitive, in our opinion, at least, because it lets you kind of from the rollups perspective apply very kind of like domain-specific constraints on the sequencing supply chain that the data has to flow through. And this is kind of a very simple example of like, we're just going to sort it, but you can do kind of more complicated stuff. Something we're working on is a PBS-style block auction. And so like, we're able, because so there's a few things that this enables about PBS style block auctions that is kind of unique to lazy sequencing that we think is valuable. One is like, because the consensus doesn't like have a concept of like the headers that are generated at the time that the data is kind of finalized, you can have an auction that only works on like part of the block. So like one way to think about it is like you can auction only like the top of block bundle, which is the example I'll go through, but like kind of more general way to think about this is you can think about your rollup as having like different functionality, and you're going to auction off like a specific functionality. And then as long as that kind of like bundle is included by the sequencing layer, you can, when you get the bytes, you can like look for the bundle that's like designated to that specific functionality and execute that for that. And so like one kind of useful thing to keep in mind here that I think Dan mentioned as well is like Oracle extractable value. And so you can say like, I'm gonna auction off the liquidation separately, and then as long as the liquidation call data is included in the sequencing layer, when the rollup actually gets the block, it's gonna look for the liquidation call data, and it's gonna restrict the liquidation functionality to that transaction. Another interesting aspect here is the rollup specific versus cross rollup auction aspect of this, where you're auctioning off essentially like a privileged bundle, and all you require from the sequencer is inclusion. Because the sequencer doesn't care about kind of what the data is, it's just data. You can have a bundle that is auctioned off that has transactions from multiple rollups at once. There's kind of hairy details in there of how do you actually coordinate this amongst different rollups, but kind of conceptually you can think about it in those terms. And yeah, I will note this is still under development. We're aiming to get this on testnet kind of before Christmas. The code is being reviewed right now. And you can think about this as, let me actually go back to, how do I go back on the slides here? Oh, okay, yeah, it wasn't working. So I'm gonna go kind of to the start real quick. So kind of in the regular, the regular kind of way the system works without the block auction is you have kind of these rollup nodes, and they have a sidecar that we're calling the composer, and that kind of gets fed transactions that have been like checked for validity by the rollup node, and then it bundles those up and submits them to the sequencer. But the sequencer doesn't really restrict who can like write to which namespace or not, and this is kind of like a nicety of the like the gas station protocol that we have there. But like anyone can create their own rollup transaction, put that into a bundle and submit that to the sequencer without necessarily going through like a rollup node. Because again, like the sequencer is kind of a decentralized like CompBFT network. And so anyone can write data to this, to the namespace for the sequencer. And so what we do for the block auction is, you can think about this as kind of like a red box and a green box, where like the green box is the gas station or like kind of someone else writing bundles, and the red box is the auctioneer for the block auction. And the auctioneer is going to run an auction that determines which transactions actually go into the bundle that it's going to post. And then it's only going to post like this kind of like top of block bundle. Whereas anyone else can kind of still post data to the namespace. And this allows you to kind of auction off like a specific part of the block, essentially. And again, like if we go back to, right, like here we had the finalized block, we deserialized this, and then we did the sequencing rule stuff to it, we executed it, and we got the header. Here we're going to do a very similar thing. We're going to look at the finalized block data. We're going to validate all the inclusion proofs, of course. And then we're going to deserialize this. In there, it's going to have kind of a transaction object and also like a bundle, an auction-winning bundle kind of object that has like the bundle that won plus the metadata. And then kind of the sequencing rule that we apply here, very naively, would be kind of you take the auction-winning bundle, you validate that it's like auctioned off by the correct entity, or kind of, if you generalize this a bit more, whatever kind of like validation checks you want to perform on this bundle, and then you unbundle them and you put them in the top of the block. And so, you start with like the data that was sequenced, and kind of the like finalized block data looks like this, but which has like transaction 0 and then the bundle and then transaction 1. But then the block that's actually executed is like 2, 3, 4 and then 0, 1. Because 2, 3, 4 is the bundle that kind of won the auction. And yeah, this is very like generalizable in that like you don't have to necessarily like unbundle it and put it at the top of the block. You can say like, the data in this bundle is going to be the liquidation. And so I'm going to like first do the liquidation, and then after that I'm going to do like a different piece of functionality kind of thing. And a nice thing about this is like you can do this like specifically at the rollup level, where the only dependence on the decentralized sequencer network is kind of an inclusion guarantee. And there's different ways of getting inclusion guarantees, which is a whole topic, but essentially like, you can have kind of multiple rollups running like domain-specific auctions at the same time on the same decentralized sequencer. You can have multiple rollups participating in the same auction at the same time on the decentralized sequencer. You can have both. It's very like modular, for lack of a better term. And didn't do this alone. Thanks to everyone else in the Astra team. I listed as many people as fit in the slide, but I think we're like 20-something people at this point. Thank you.
Thank you, Itamar. We have time for questions.
Hey. Yeah, thanks for the talk. I was just curious, so given you have the kind of sequencing network and it's separate from the DA network, is there a construction where if one of those two goes down, you're able to kind of rely just on one of them to produce blocks, or how's the redundancy built in there?
So, I mean, the sequencing network has to be running because when you're validating the inclusion proof, so you're making sure that the block data was kind of included in a sequencer block. But in case that that you don't want to connect to the DA network, you don't have to. You can operate kind of only on the soft blocks, which is very nice if you're trying to do a more kind of like latency optimized thing and you want to execute blocks kind of as soon as they come. It's actually like something we leverage in the block auction, where we're able to like kind of like tie the auctioneer straight into the sequencing node, where you can kind of start an auction optimistically before even though you have single cell finality, you can start the auction kind of as soon as a block is proposed, kind of, and then you like reorg like if there's multiple rounds of kind of voting or something like that, you can kind of reset your auction and restart it, and you buy a few hundred milliseconds with that. Yep.
Cool. And if the sequencing network is censoring someone, they wouldn't be able to just send a transaction to the DA network to get it included, or is there like a forced transaction path there?
So that's something we've definitely looked at. We haven't explicitly like implemented yet because we've been focused on like launching a mainnet, and like we'll worry about how you work if the mainnet falls like kind of later on. But it is on the roadmap to figure that out. Yeah, I think like Celestia has a few interesting developments with like their like lazy bridging module and things like that that will make that very doable.
Thanks.
Oh, I'm wondering about execution speeds from going essentially from like a sequencer bundle to the DA blob, and what are the different performance bottlenecks on the right path?
So you mean from like the point that a bundle is posted to the sequencer through the data? So you end up with like bundles are kind of regular transactions from the sequencing network's perspective. And it's a COM-EFT chain, so it gets these bundles. It comes to, like it builds a block out of that, which is like kind of which bundles are in my mempool. I'm gonna like put them in some order, create the like, sort it into namespaces, create the inclusion proofs, that kind of thing. And then these are kind of like, at the same time, once the block is finalized, because you have like single cell finality, the block is sent to the rollup node, but then there's also kind of like a DA relayer component that kind of like batches them and makes sure that we post them like once per block to the DA network. Does that answer your question?
Yeah. Thank you.
Okay, I have some pretty naive questions, but first of all, the DA layer is specifically Celestia. It's not like abstracted as far as I understand. And given that, is the sort of the vision like there will be this zone of, from the perspective of Ethereum, these are validiums because the DA layer isn't ETH, and this zone of validiums could all synchronously compose to each other as long as all of them share the same Celestia DA sort of property? Is that?
No, like the DA layer is kind of abstracted from the perspective of the sequencing layer. There's like there's a aspect that's kind of responsible for posting the data to Celestia. We're kind of like a Celestia ecosystem kind of project, so we started off with that, but it is sufficiently abstracted where you just post these to blobs if you want, yeah.
Oh, okay, so it's abstracted enough that this could be for many different
as long
DA
as it's
types.
bytes, yeah.
Okay, cool, thanks.
Depends on like the inclusion guarantee you have. Like blobs on Ethereum are kind of very like bare bones, whereas like Celestia has the data availability sampling thing, which allows them to like, you can do much larger blocks and retrieve them more efficiently. So we kind of just went with that. But as once like dank sharding is added and things like that, like there will be kind of a reason to leverage ETH as well.
Yeah, in such a world where you are posting to the to things that use Ethereum DA, can you synchronously compose with the L1 then inside of these sequencer blocks, or?
Yeah, so that's like complicated issue. We do have like a bridging protocol between rollups and the sequencer and across rollups. And so like, we haven't really worked on getting this deployed on Ethereum, but like, conceptually you could, yeah.
Okay, cool, thanks.
Hey, thanks for the talk. Question: as sequences are lazily not executing because lazy sequencers, is there a concern on the number of nodes that can catch up to the tip of the chain? And if users are transacting on the tip of the chain, how do they get the state?
Do you mean rollup nodes or sequencer nodes?
I'm just thinking about a user who's running a full node trying to make a transaction.
So like from a sequencer node's perspective, because you think about it like you're only coming to consensus over just like bytes and which bytes are in the block, instead of also taking those bytes and like deserializing them, executing them, and so on. And so it's kind of just like faster than doing the more work. And then from the rollup node's perspective, there's kind of obviously like real world kind of performance questions of like I don't know, we tried to like do sub-second block times a few weeks ago, and Geth just started crashing because the like type of the timestamp is like an integer there, and so if you're less than 1, like it gets like weird errors, and so you know, there's like real world problems like that, but like theoretically, you know, you could just feed the thing data, execute it, and move on. Yeah.
Is there a scenario in which the sequencers are just building blocks so fast that very few other roll-up nodes can catch up and?
I don't think so. That seems like a very like good problem to have if we can get the sequencing network to like finalize blocks that fast. But I don't think, like, if you think about it, right, like taking a bunch of bytes, deserializing them, executing them is a lot less work than like taking a bunch of bytes, serializing them, sending them over the network, receiving them, deserializing them, checking them for stuff, and then sending out a vote and like doing what is involved in consensus. Like you have both kind of more compute involved potentially, or I guess not necessarily because you don't do the execution, but like you have kind of a lot more network throughput that's involved, and so that would kind of be like you know, to a degree like much slower than just getting the bytes and executing them.
Yeah. Thanks for the answer.
Thank you, Tamar, again.
Thank you.
So we're going to take a break right now. I believe there are refreshments downstairs on the first floor, but also if you just want to network and chat, there's some nice tables outside and so on. We will reconvene here in 25 minutes at 10:40.